Good morning. We are again streaming. I'm sorry about the white background. I just got a little bit of feedback. People started yelling at me, making me cry, but I'll struggle through it. So if you can follow along, that's great. If you want to go and flip to something else, like watch, I don't know, Law and Order or something like that, go ahead. Alrighty, and we will begin.
Alright, I'm Braden.
I'm Matthew.
And we did our calculus project on the Avengers Agents of Calculus.
Alright, so why we chose the Avengers. First of all, both of us are huge fans of the Avengers. Second, we wanted to check if the Avengers are realistic or unrealistic. And the Avengers Infinity War was just released and is very popular because the domestic total is over 600 million. Alright, so some background on the Avengers. We split it up into comics and movies. Under the comics, they're a team of superheroes first appearing in Marvel comic books. Stan Lee and Jack Kirby revised the All-Winners squad into the current-day Avengers in 1964, and the Avengers originally consisted of Ant-Man, the Hulk, Iron Man, and the Wasp. And the Avengers first appeared in The Avengers #1 in September of 1963. For the movie side, the Avengers were launched with the Marvel Cinematic Universe in 2008 with Iron Man, and the first Avengers movie was 2012, and the sequels were the Avengers Age of Ultron 2015 and the the Avengers Infinity War 2018.
So the first character we'll be analyzing is Thor, specifically his hammer. So Thor's hammer is based off Mjolnir, which is the weapon of the mythical Thor. It first appears in Journey into Mystery number 83, which debuted in August of 1962. It was created by writer Stan Lee and designed by artist Jack Kirby and Joe Sinnott. And then the saying that goes along with the hammer is, "Whoever holds this hammer, if he be worthy, shall possess the power of Thor." So the main thing we're looking to do with Thor's hammer is find the volume, and specifically just this part right here. And so the hard part about it is that Thor's hammer is unique because it has these beveled edges. And so we cannot just use like a regular volume like formula, so we can't just do base times height. So instead, since they have cross sections of square, we're gonna find out the volume using cross sections of squares perpendicular to the x-axis. So using the dimensions found on the previous page, we put these points into GeoGebra, and then after we put all these points in, we need to find the equations of lines AC, C to E, and then E to F. So this is our work for equation of line AC, and then we found C to E just to be y equals 6.8, and then E to F is the equations right here. And so in order to find the volume of Thor's hammer using cross sections, we use the equation times by 2 since it's perpendicular to the x-axis, and then we squared it and then integrated from 0 to 1.3 for just that first section over there. And then next we did the middle section, we did 2 times 6.8 squared, and then integrated it from 1.3 to 17.6. And then for the last portion from 17.6 to 18.9, we integrated it and then we times it by 2 and then squared it. And that reaches our total volume of 3,384.494 centimeters cubed, which we're pretty sure is correct because we did an overestimate by just adding these squares on and just using a regular volume formula, and that was about 3,400 centimeters cubed.
Alright, so our second character we used was Captain America. And Captain America has his shield for his primary defense and weapon of Captain America. Originally he had the heater shield, which appeared in Captain America Comics #1, March of 1941, and then it evolved into his circular shield, which is best known for Captain America, which debuted in the next issue. And he was created by writer Stan Lee. Alright, so before we show this clip, we had to find a clip throughout any of the Avengers movies where the camera was not moving or following the shield to make sure that we could use capstone to measure out the exact flight of the shield. So I'll play that. Yeah.
Look at the time.
It's very dramatic.
Please don't make me do this.
That's all you get. All right. So, using Capstone, we were able to map out the exact flight of the shield. And in Capstone, you need to define like a reference height. So using Bucky, who is 6 feet tall, we measured him out to be 1.83 meters to make sure that we use the same reference point for all of our points. Using this data, we created 2 graphs, one height with respect to time from 0 to 0.3, and the second being horizontal distance with respect to time, 0.0 to 0.3. And the x-axis on both of them being time, and on this one, the y being height, and on this one, horizontal distance is our y. All right, next, the calculus of the shield. So first we had to create an equation for the height of the shield with respect to time, which is equal to f of t. And next we created the equation for horizontal distance with respect to time, g of t. To find the average horizontal velocity, we took g prime of t, integrated it from 0 to 0.306 and divided it by 0.306 to equal around 15.424 meters per second. Next, we needed to find the time which the maximum height occurred. So taking f prime of t, we set that equal to 0 and found out that around 0.25 there was an extrema. So because it was increasing from 0 to 0.25 and decreasing from 0.25 to 0.306, we concluded that there was a relative max at time equals 0.25 seconds. And as shown in the previous slide, we found the distance between Bucky and Captain America to be around 7.41 meters. So using that, we set 7.41 meters to g of t to find out that the flight of the shield took about 0.48 seconds before it hit Bucky.
So the next character we're going to focus on is Iron Man. So Anthony Edward, or Tony Stark, suffers a severe chest injury, and then he creates the suit to save his life. After this event, he creates a new suit and becomes Iron Man. And he first appears in Tales of Suspense number 39 of March of 1963, and he's created by writer Stan Lee. Now for this clip, this one is probably the one that's most inaccurate. It probably has the biggest wide margin of error, but we really wanted to include it because we had to take a specific approach to this. Mr. Kruger, I don't know if you remember this, but there was a time where I had a problem on a question. I went up and I asked you, and you're like, when we did it was actually pretty easy, but I had to just look at it from a different angle. So that's kind of what we had to do with this video here. A lot of explosions in this one. Yeah, so we're going to be measuring this part right here. Alright, so as Matt mentioned before, like with Capstone, you need to have a specific reference height or whatever. But with this, it's hard to find a specific reference height because it's from such far distance, and there's no way to really tell how tall these mountains are. So we went about it in 2 different ways. The first way, we tried to find out what the height of this explosion was. So through research, we tried to find at about at what time would explosion be this height. So after looking online, we figured out we couldn't really figure that out because there's no way to figure out what type of explosion it was, and also the different way to which the flame grows was varied greatly online. Like there's one that was 80 meters per second, and then there's one all the way up to 1,000 meters per second. So we knew we couldn't do that. So what we did then, we timed the scene right after that. He starts falling to the earth. So with the basic acceleration due to gravity of negative 9.8, we took the antiderivative, which was the velocity equals negative 9.8 t, and then there would be no plus c because he had no initial velocity when he created a turning point. Then we took the antiderivative again and got negative 4.9 t squared plus c, and then we plugged in 5.62 because that was the time it took for Iron Man to fall to the ground. And then we squared that and we found c to be about 154.764 meters high, and so that's what we used there. And so using Capstone, we marked all the points that we could with Iron Man, and we created 2 graphs. The first one being horizontal distance with respect to time, and the second being height with respect to time. For the top graph, the y-axis is the horizontal distance, and the x-axis is the time, and then for the second graph, the y-axis is the height, and the x-axis is the time. And then for both of these, we're only looking at the interval from 0 to 2. And so we define horizontal distance with respect to time as f of t, and that's the equation right there. And then the height of Iron Man with respect to time, we had g of t. So in order to find the average horizontal velocity, we integrated f prime of t from 0 to 2.107, then divided it all by 2.107. We got his average horizontal velocity to be about 20.0255 meters per second. And then average vertical velocity, we integrated g prime of t from 0 to 2.107, and then divided by 2.107, and got it 36.223 meters per second. And then during that video, he is mainly traveling in a northwest direction, so we wanted to find out his velocity while going northwest. So we used Pythagorean theorem, and we used one leg as the average horizontal velocity and the other one as the average vertical velocity, and we got his velocity going northwest to be 41.39 meters per second. So this is when our presentation takes a little bit of a turn. So we wanted to compare the Avengers to a real life person, so we chose Mr. Kruger, primarily for two reasons. The first one, we didn't want to choose me or Max, so we didn't want to make the data biased. And then the second reason, Kruger, you might be close to retirement, so if you want to be a part of the Avengers, this could be like an application for you.
All right, so a brief history of Mr. Kruger. So there's three main ones. His favorite number is 3, his dog's name is Rosie, and he's a calculus fanatic. All right, so first we wanted to look at Mr. Kruger's pen, which is probably his weapon of choice. So we traced half of his pen on normal graph paper and then plotted different points along that outline to create an equation on one of our calculators. The equation is equal to f of t, so we revolved it around the x-axis. So we took f of x squared, integrated it from 0 to 14.7, multiplied it by pi to get roughly around 18.937 centimeters cubed, which is about half a percentage of Thor's volume of his hammer. So even though it is a little bit smaller, you could argue that the pen is mightier than the sword, or in this case, the hammer. All right, and our next character was Captain America. So we wanted to measure Kruger's throw of a frisbee, which is kind of the same as a shield. So we'll show you this clip. And a special shout out to Ella Benoit for catching this. She did a fantastic job catching it. So thank you, Ella. I'll show it again. All right. All right, so after we took this video, we could put it in capstone to measure out, or to plot each point of the flight of the disc, as shown by the red crosshairs. And since we took this video ourselves, we could put a meter stick to make sure that we had the 1 meter reference point instead of trying to figure out where it would be on the video itself. And using all of this data, we created a graph, horizontal distance with respect to time, x being time and y being the horizontal distance. And we're looking at that from 0 to 1. So the calculus behind his throw, we could find the total distance of the frisbee with respect to time by f of t, and the average velocity. We found the average velocity by taking the by integrating f prime of t from 0 to 1.021 and dividing it by 1.021 to equal about 5.933 meters per second. And Captain America's flight of his disc was 15.424 meters per second. So Mr. Kruger's throw was about 40% of Captain America's, which in time will increase, and he will get to that point.
All right, the next thing, in order to compare to Iron Man, we will map Kruger's walk to see his velocity. So if you play the video. Yeah. So Kruger's getting ready here. Alex.
Gotta warm up.
Yeah, and this is not slow motion. This is real speed, actually. So. And there we go, right there. And so in capstone, we measured the points like we did before, and then we were able to develop an equation with horizontal distance being the y-axis and the x-axis being respect to time, and then we're only looking at the interval from 0 to 7. And then the calculus of this, we define that graph as f of t. In order to find average velocity, we did the derivative of f of t and then integrated from 0 to 7.879, then divided it by 7.879. We got his average velocity to be about 1.01 meters per second, which is only about like 1/40th of Iron Man's speed, but maybe if you had a suit, you'd get there. And so next we looked at acceleration. So we looked at the second derivative and set that equal to 0 to see where t equals 0. And we found at about t equals 3.256889, that's about when his acceleration, or the second derivative equals 0. So we looked at the two intervals from 0 to that about 3 second spot, and then that 3 second spot to about 7.879. We found he's accelerating from the first interval and then he's decreasing in the second interval. And also at time equals 1 second, he's accelerating at a rate of 0.0748883 meters per second. And so in conclusion, we kind of figured that the Avengers were actually pretty realistic, except for the exception of Iron Man. With Iron Man, we found his velocity to actually be kind of slower than what really it should be, because the rate of this flame, it should be at least 80 meters per second. But so where we think the error was in the movie is that it should have taken him longer to fall to the ground, so that would have contributed to a higher height, and therefore would have gave us a better reference to find the height. So some frustrations we had during this whole process. There's limited footage, so we could only use the footage that was in the movies, and we couldn't just go out and create the footage. And a lot of the footage was too fast to map anyways. The second part was hard to find a reference point, and that was specifically seen with Iron Man. The third part was that we had to use multiple equations. We had to use one for height and then one for horizontal distance. And the last one, neither of us knew physics too well, and we had to deal with a lot of physics concepts. Do you have any questions?